If you build AI agents today, you quickly hit a wall. The core capabilities of your agent aren't in one place. They are scattered across entirely different layers of code. You write prompt templates in text strings. You define tools using JSON schemas. You wire up the actual logic in application callbacks. And you manage the overall state using workflow graphs. To tie these different formats together, every modern framework invents its own domain-specific language, or DSL. This creates a bottleneck. Instead of using native programming features, you are forced to use custom abstractions for scoping, state, and control flow. This exacts a heavy toll on the developer. Every new framework requires you to learn its bespoke syntax just to do things that Python already handles natively. But the worst tax is paid by the AI itself. The language model never saw this custom DSL in its training data. So you have to teach it the rules at inference time, stuffing your prompt with formatting instructions. That burns tokens and invites formatting hallucinations. A new paper out of NVIDIA called NOOA proposes a clean break from this model. The solution is to define the agent strictly as a native Python class. Python works because the LLM has already mastered it during its pre-training phase. When you use the code patterns it already knows, zero in-prompt instruction is required. Moving from a fragmented architecture to a zero DSL agent starts with a direct one-to-one mapping. A NOOA agent is simply a Python class that subclasses an agent base object. The instance fields act as the model visible state, and the class docstrings serve directly as system prompts. Tool schemas are absorbed by type annotations, forming a strict contract. Finally, the method bodies become the executable actions. This setup requires a way to distinguish normal code from code the LLM needs to handle. If a method has a real code body, it runs deterministically as ordinary Python. But if the method body contains only the literal ellipsis, 3 dots, the harness intercepts it and turns it into an LLM-driven loop. Detecting those 3 dots requires an abstract syntax tree, or AST, walk. The AST is the structural map of the parsed source code, and navigating it is how the framework identifies an agentic method. A naive string check would fail. Inspecting the code directly often returns the decorator lines, and an agentic method usually starts with a docstring. The parser has to walk the tree, stripping out the docstring expression to isolate the standalone ellipsis. Once the parser confirms the method body is exactly one ellipsis expression, the framework steps in. It intercepts the call and hands control over to the language model without forcing the developer out of their IDE. The developer factors the agent at the method boundary. The model sees a uniform API surface. Defining the class is only the first step. Every turn, the framework has to render the live state of this Python object into context so the LLM can read it. This diagram shows how NOOA renders context in 3 specific regions: the static prefix, the event history, and the dynamic tail. The static region contains system instructions and the agent's docstring, remaining immutable, locked into the GPU cache. The event history sits right beneath it. This region strictly appends new logs of tool calls and outputs. Because it only grows downward, the cached static block above it remains perfectly intact. Finally, we have the dynamic region. This contains volatile Python expressions that must be reevaluated on every single turn. This data is intentionally placed at the absolute tail of the prompt. This order is dictated by KV cache invalidation physics. In large language models, changing a single token invalidates the cache for all tokens that follow it. If volatile dynamic data is placed in the middle of the prompt, it constantly shifts. That movement breaks the cached prefix every single turn, forcing the model to re-encode the instructions from scratch. The context layout here is a strict topological choice, optimized for provider caching constraints. It ensures the most stable data is always first, and the most volatile data is last. Even with optimized caching, traditional frameworks hit a wall with data size. If an agent tries to process a 1,000,000-row table, serializing all that text into a JSON prompt causes context bloat and catastrophic failure. NOOA bypasses the context window using pass-by-reference previews. To process large inputs, the framework separates where the data lives from what the model actually sees. The massive live object stays bound in the local Python execution environment, the REPL namespace. Instead of moving the data, the framework sends a bounded preview string into the LLM context window. This text contains only the concrete type, the true length, and a tiny sample of the head and tail. The LLM reads the preview to understand the shape of the data. Then it writes standard Python code, like requesting the sum of a list, to query it. The framework fires that code back into the local namespace, executing it directly against the massive live object, and returns only the final answer to the model. This contrasts with standard model context protocol integrations, which force serialized text responses across the boundary, dumping the entire result directly into the prompt. Keeping the data in the namespace means the volume of processable data is bounded by the local execution environment. Pass by reference decouples the agent's processing capability from its token limit. With context optimized and data in place, the agent enters its iterative execution loop. The critical question is, how does an autonomous agent reliably know when its task is finished? In most frameworks, agents declare completion simply by stopping their tool calls. The model decides it has nothing left to do, halts, and outputs a response. This convention leads to high failure rates and premature, unsupported completion claims on complex tasks. NOOA replaces that convention with a code-act loop. Each turn, the model must choose between two primary paths. It can execute Python code in the restricted REPL, or it can call a specific action to return a result. When the model decides it is finished and attempts to return a result, the output hits a locked toll gate based on the function's type annotations. The framework executes a strict programmatic type check to validate the model's proposed answer against the exact return type required by the developer's contract. If the type doesn't match the contract, a validation error is injected back into the prompt and the loop is forced to continue. This transforms a passive code annotation into an active, executable guardrail. A NOOA agent cannot declare a task complete without a valid result. It is forced to prove its work against the predefined interface before the framework allows the loop to end. On the SWE-bench benchmark, NOOA achieved an 82.2% pass rate, establishing a new state-of-the-art among open-source harnesses. And it reached that score while cutting token consumption roughly in half, requiring only 1.1 million tokens per task. That drop in tokens is the direct result of keeping large objects out of the prompt, using pass-by-reference previews. But securing these metrics requires a specific engineering trade-off. To keep live objects in the local namespace, the model-written code must be executed in the agent's own process. Because the framework runs code locally rather than passing serialized copies across a boundary, the system sandbox must go around the entire host process, not just the isolated function. The validator protects the loop, but it does not protect the host. Furthermore, the empirical data shows this advantage narrows as base models apply more reasoning effort. The smarter the underlying model gets, the less it relies on the harness to maintain discipline. Yet the core philosophy holds. Alignment with the model's pre-training data is superior to inventing abstraction layers. By collapsing fragmented custom languages into a native Python object, NOOA produces faster execution, token efficiency, and programmatic reliability. It shows that the most effective framework is often the language the model already speaks.